I guess there's a. I guess then I'm also. So, all right, excellent. Thanks. So I would like to know what people think about this setup here. I mean, now all the chairs are sort of moved forward. So you have not as much leg room, but I guess I sort of feel like I'm talking to a group of people as opposed to a very big group of empty seats. So I'm curious. I'm curious what people think about this. And you can tell me after the class. So last class we talked about Eulerian graphs and Eulerian tours. And there's a little bit more that I'd like to say about that. And if there's time at the end of class, I'll talk about it. But I think that so that we can have a really coherent class, I'm going to start talking about planar graphs. So who knows what, just so that I can get a sense of how fast or slow I should talk. Who knows what a planar graph is? So like higher, so I can get a. So maybe 3 or 4 people. How many people don't know what a planar graph is? All right, neat. Okay, so planar graphs. I'm trying to decide whether I want to use whether I want to draw or use Professor Skeena's slides. I think I'll start. I'll start just using the original slides I was given. So graphs really are combinatorial objects. I mean, just points and lines, or we can view them as sets of elements and sets of pairs of elements. But there's a separate problem, which is the problem of how to draw graphs. You can imagine if I give you a graph, then there are lots and lots and lots of different ways of drawing it. And you could look at this graph at 2 different drawings, and you wouldn't even recognize that it's the same graph. And in fact, what I wish I had thought to do, turns out there's actually a whole book written on the problem of how to draw graphs. And there's whole conferences where the goal of the conference is to figure out how to draw graphs. And ideally, when you're drawing a graph, in certain cases, you might want to have you might want to draw different graphs for different purposes. For example, it might be important for you to draw a graph that is composed of straight lines instead of curves. Or in another case, you might want to draw a graph where it's easier to convey the information if you use curves rather than a straight line. I'm trying to think what would be a good example. I mean, I guess if you drew this graph here, I guess a smiley face graph, then probably information is lost if you don't have the curves in there. One important class of graphs is called planar graphs. And in a planar graph, the idea is that we can draw the graph in the plane in such a way that no edges overlap, no edges intersect. So, as Professor Skeena says, although graphs are purely combinatorial objects, it is hard to separate our visualization, the drawing, from the underlying structure. And then he defines a graph G as planar if there's a way to draw it in the plane so that no edges cross except, at the vertices. It doesn't mean, so a graph is purely combinatorial. So the point is that this graph here, it turns out, is a planar graph, even though it intersects, because there's another way of drawing the same graph so that it doesn't intersect. In particular, if we if we take this line, remove it, and put it over here, and take this line and put it here, and take this line and remove it and put it around here, then you see that there actually is a way to draw the graph so that no edges intersect. So Professor Skeena makes a distinction between a planar graph, which is defined here, and a plane graph. So I'm not sure how, I guess I should dwell on this for a little bit. So a graph is planar is something combinatorial about the structure, and a drawing of a graph is a plane graph if, along with the graph, how should I say it? Such a drawing is an embedding of G. Any graph with its embedding is called a plane graph. So this is the planar graph. When you consider the particular embedding into the plane, then it's called a plane graph. And as he points out, there could be many, many different ways that we choose to draw the graph so that it still ends up being a plane embedding. For example, this edge here, we could have chosen not to draw it here, but sorry, not this one. We could have chosen AF rather than having it go around this side of the structure. We could have had it go around that side of the structure. So I guess the first so let's see. Let me just say quickly. So we're talking about planar graphs, and the graph is planar if there exists a way to draw the graph in the plane so that no edges overlap. So this graph here is a planar graph because we could redraw the edges in such a way that there's no overlapping. So there's a large amount of freedom in how we draw planar graphs. For example, we could move this edge AF in any one of multiple directions. Right, so that's a very interesting question, and I'm glad you asked it. So the question is, are you allowed to move vertices? And the answer is yes. You're allowed to place the vertices on the edges however you want. And placing the vertices is maybe even the harder step, in that the placement of the vertices somehow defines the architecture, and then the edges are kind of like the beams between the various places. So maybe it's even harder to figure out the right way to place the vertices. One final point, which is, notice that this planar graph here has got curved edges. It turns out that it's a very interesting theorem that says that any planar graph can be drawn so that the edges are actually straight. So we can kind of move the nodes to straighten the edges. And so if we were going to do this here, we might want to move this edge D farther up so this doesn't curve so much. And we can move this edge C farther down so this doesn't curve so much. So I guess if we were going to draw this so that it's straight, how would we do it? I guess we would draw a straight edge from A to E. then maybe I would put D here. And then what would I do? I guess I would put B here and make an edge from B to D. And then, where should I put F? So let's see. So I could put F here. And I'll put F here. Because F has got to be to A, so why don't we put F here? So go like that. And now that's pretty straight. And then C has to be connected to E. So here? So right here. So put C here. Yeah, so this is not the most beautiful picture, but I guess it communicates the idea that we can move things in such a way that all the edges are straight. And already that's a pretty amazing idea. Uh-huh. Oh, so like there. Let's see. Hard. I mean, I guess the main idea is that we would sort of want to move how would we do it? We sort of put F around here so that we can go. I'm not sure. So yeah, so this should be okay. So already there's that's a beautiful theorem. It's not obvious that this is possible, but it turns out that it is possible. But planar graphs are very amazingly structured, and there are a lot of amazing simple properties. And so this is just the beginning of what I'm going to talk about today. Did someone raise a hand? All right. So there are lots of different ways of okay, so that's the main definition. What I just described is the main definition of a planar graph. It turns out there are lots of other ways of defining a planar graph. And I'll show you another way of defining it, which, as Professor Skinner writes, comes from the slums of topology. So apparently, the Whitehead once called graph theory the slums of topology because he thought that planarity was really a topological problem. And if you look at this picture here, you can kind of see that he might be right. Or at least this is another way to define what we mean by planarity. So the point is this. Actually, I wonder if I have a yellow pen. So another way that we could define a planar graph is we take a convex object here. I'll just read what he wrote first, and then I'll explain it. So embedding graphs in the plane is the same as embedding them on a sphere, and then you sort of clip off a point. So you can embed the graph on a sphere, and then, or like a balloon, and then kind of pop one end of it. And another way to describe it is equivalently, every convex polyhedron defines a graph. So where the vertices of the polyhedron correspond to vertices of the graph, and the edges correspond to edges of the graph. And we can go from the polyhedron to the graph by putting a light here and looking at the shadow that you get on the plane from this light. And if you think about it, I mean, it's not obvious. But why would it be that if you put a light on the top, that there are no overlapping shadows of the edges? I mean, can anyone see why this would be? It's not obvious, and I still don't think that I know the best way to explain it. But can anybody think why no two shadows would overlap? And what's important is that it's convex. Can anyone think why that would be? And if you want to think about it, I also don't mind if you talk to your neighbor. Just this once. Not. I mean, I don't know. Does this make intuitive sense, or is this just sort of... Why would that be? Yeah.
In order for an edge to come back in around, it would be less than, it wouldn't be able to be convex.
Yeah.
Because the shape would have to go out and then come back down around underneath the light source again.
Yeah, exactly. I mean, right on the ball. And basically, I mean, just to say what, if ever you had something that overlapped, then somehow, if something overlaps, then would mean that the beam of in one place, the beam of light would have had to leave the polygon and then come back into it. At least in one of these four places, in order to get this, the light would have had to go out of the polygon and then come back into it. But the definition of convex means that any beam of light, once it leaves the polygon, it doesn't go back into it. And the place to look for this is that in one of these four corners, or places right around there, that's got to happen in order for it to cross. Does that make sense? I don't know. Does that make sense? I think it makes sense to two people. But I'd at least like to bring that up to a constant fraction.
Do you have a constant fraction?
All right, sounds good. So like about 1 over, or 2 over 30, right? That's the constant fraction. All right. So the constant fraction will stay at what it is unless people ask for more. Okay. So now we've talked about various ways of defining by planarity. And now let me describe a couple more characteristics of planar graphs. So a planar graph So let's say that a planar graph has V nodes, R faces, and E edges. So one question that we might want to ask is, what is the relationship between these three values? What's the relationship between V and R and E? And actually here I said planar graph, but really I should probably say plane graph, because it could be that different embeddings of a graph might have different number of faces. Although clearly every embedding will have the same number of edges and the same number of nodes, but the number of faces a priori could be different. And I mean, I guess I would want to put more suspense, but since I know that all of the slides have been handed out to you, I guess that the suspense is already has already been evaporated. So let me just point out what the relationship actually is. So this is Euler's formula. So there is a very beautiful relationship between the number of vertices, edges, and regions in planar graphs. And in particular, this is that the number of vertices minus the number of edges plus the number of faces is 2. Always. And if we want to, yeah.
What's a face? What's a face?
Oh, right. Okay. That's a very excellent question. So by face, maybe I should say instead of face, I should say region. So if you have a planar graph here, then there are 3 regions. You know, region 1, region 2, and the whole outside is region 3. So the question is, what is the relationship between the number of regions, the number of vertices, and the number of edges? And if we look at a tree has n vertices, and because it's a tree, you have edges that connect all of the vertices together. And so there are n minus 1 edges. And in a tree, there's actually only one region, which is just the outside. There's no other regions that the edges contain. So if we add this together, the number of vertices is n, minus the number of edges, which is n minus 1, plus one region is 2. And then Steve also gives this example of a cycle. So a cycle has n nodes, n edges, and 2 regions. So this region outside and this region inside. And I mean, he writes just what I said earlier, that by convention, and especially for the construction as in the previous page, we always count the outside of the graph as a region as well, sort of at the point at infinity. And this says that the number of regions really is an important quantity, something that's combinatorially important, because this implies that the number of regions of any planar graph is independent of the particular embedding that you choose in the plane. So this is the illustration. So this is an illustration of Euler's formula, saying what it is and giving two illustrations. But let's see how to prove it. I mean, without looking at the next page, what would you think is the best way to prove this? Induction. Absolutely. This really isn't very good. I'm not sure if I'm supposed to stand on stage and broadcast, but it says real fruit beverage. But so there's 5% fruit in this thing, which I guess is better than, I don't know if you've looked, have you ever looked at, they sell Country Time lemonade all over the campus. Did you know it doesn't contain any fruit at all? So anyway, I guess I shouldn't get that again. So how would we, so suppose we were going to do this by induction. I'll show you the proof in just a second, but let me see if I can motivate it. First on this picture here. Let's see. Let me see if I can give some sort of motivation drawing here where the induction, where the proof would come from. Suppose we take this graph here and decide to add an edge to it. One thing we could do is just to add an edge like this. Now look at what's happened. We've added a new vertex, and we've also added a new edge. And so this quantity should stay the same. We could add another vertex and another edge, but of course the quantity is going to stay the same again. You add a vertex and then you subtract an edge from it. Now what happens if we make a new face? Well, the way to make a new face is to combine two existing nodes that weren't previously connected. So, for example, we could combine those two nodes there. And if we combine these two nodes, you notice we're adding a new edge, and we're also adding a new face. So in this quantity, what we're doing now is we make a new region, but we also add a new edge, and that gets subtracted, and so the quantity stays the same. So this is intuitively what's going on. And the reason why I want to emphasize this is, I have no idea, but this seems like the sort of quantity that you should know on an exam. And whereas it might be nice to memorize it, if you memorize it, you'll forget it. On the other hand, this concept of how you build this is such a simple thing that if ever you panic and suddenly you wake up, I don't know, at 3 a.m. from sleep, and you say, "My God, I've forgotten Euler's formula." Then you can go back to sleep happy because you can rederive it. And so that's what this picture should show. But but maybe I can say the same thing, write the proof in a more formal way. So the theorem formally is that for any planar graph, the number of vertices minus the number of edges plus the number of regions is 2. And this would be by induction, in particular by induction on the number of regions. And the base case is that this is true for trees. And it's true for trees because trees all have one region, and as we said, they have n nodes and n minus 1 edges always. So the base case is that it's true for trees when the number of regions is 0. So then if we want to pursue the inductive step, we can assume sorry, is 1. Oh yeah, so this is actually a mistake in his slides. So I don't know. Am I doing him a favor by correcting it, or am I just desecrating his? I think I'm doing him a favor. Okay, so thanks. Okay, so the number of regions is 1 in the base case, as we talked about. So for any planar graph in the inductive step, for any planar graph with less than r regions, let's assume that it satisfies this expression. And then, so any planar graph with r regions can be made by adding vertices and edges to a graph with r minus 1 regions. So now we're adding vertices and we're adding edges. And I described there are 2 cases. In the first case, you don't increase the number of regions. And instead, what you do is you add 1 node and 1 edge, and so the quantity stays the same. Or, in fact, you add an edge that connects 2 regions together. And then the number of regions goes up, but the number of edges goes up by 1, and the number of vertices stays the same. So this is the idea, a little more formally, of the proof that we talked about. And that's Euler's formula. So I don't know. Was that clear? Was that too slow? Was that... Okay, so another point about planar graphs is you really wouldn't expect that planar graphs have too many edges. In particular, I mean, if I give you if I give you edges that are really dense, nodes with lots of edges, you really wouldn't expect it to be possible to spread everything out so that you remove the crossovers. Because the more edges there are, the more chances there are for things to cross. And the less freedom you have to prevent it. So we would expect planar graphs to be rather sparse. But let's see if we can actually quantify this. And of course we don't have to, because Steve already did it for us. So as he said, it's easy to draw graphs in the plane when they have few edges, intuitively. And the more edges, the harder it is. And so we have this theorem that any planar graph on n vertices contains at most 3n minus 6 edges. So in particular, the number of edges in a planar graph is linear in the number of vertices. And of course, this isn't usually the case with graphs, because usually the number of edges could potentially be quadratic in the number of vertices. And let's see if we can prove this. And I think to prove this, I really want to rewrite it rather than to use this transparency. So let's see if we can do this. Okay. So the first comment is that if we have a planar graph, wherever there's not a triangle, wherever there's a square or something, we can add edges to make everything triangles. So if we have suppose this is our planar graph, we could have an edge to make something a triangle. If we have, keep adding edges to make things triangles. So what this means, okay, so we can keep adding edges without losing planarity until each face is a triangle. And the result is that now let's see what math we can say. Well, we can say two things. We can say that each edge touches two faces. Because this edge touches this face and this face, this edge touches. So each edge touches two faces. This edge here touches this face here, and also the face outside face. So each edge touches two faces. And the other thing that we can say is that each region is touched by at least 3 edges. In particular, all these regions on the inside are touched by 3 edges. But this outside region here is potentially touched by more than 3 edges. So now, how can we say this? I guess we should say the number of touching. So how many touchings are there? We want to describe the number of touchings. Well, since each edge touches 2 faces, then the number of touchings has got to be 2 times the number of edges, because each edge touches twice. And we can also say that the number of touchings is what? Well, each face each region is also touched by at least 3 edges. So the number of touchings is also greater than or equal to 3 times the number of regions, because each region is touched at least 3 times. So now we can set these two equal, and we get that 2 times the number of edges is greater than or equal to 3 times the number of regions. And we also know that the number of nodes plus the number of regions minus the number of edges equals 2. So here are 2 terms, and since we're trying to show what we can have in terms of edges and vertices, then we should get rid of regions. So in particular, we can say that 2 times the number of edges is greater than or equal to, actually, so let's do this, that R equals E plus 2 minus N, just moving this stuff over. So 2 times the number of edges is greater than or equal to 3 times E plus 2 minus N, which means that 3N minus 6 is greater than or equal to E. I decided to plow very slowly through this algebra because I think it is pretty important algebra, and it's stuff that you should really know, and know enough to be able to recreate. Now I guess I can put, I'm not sure if it's even necessary, but I can put the original slide on. And this is, this is really all the algebra you need, but I really wanted to put in steps and wanted to recreate it because this is stuff that I want people to remember. And of course, okay, so now that I've just showed how to, from these 2 expressions, how we can solve to figure out the number of edges in terms of the number of nodes. But one could potentially also solve for the number of regions. So in this case, we would get rid of the number of edges, so we could describe the number of regions in terms of the number of nodes. And here I think I'm just going to explain and walk through the algebra rather than redoing it, because it's the same idea. So as before, there are 2 equations. N plus R minus E equals 2. So R equals, just solving for R equals E minus N plus 2. And then since we're trying to get rid of E, we can just plug in and for E equals 3r divided by 2 minus n plus 2. And basically, we can solve for r to get something which is less than or equal to 2n minus 4. I don't know, I can go into more detail on the algebra, but it's exactly the same idea as I described earlier. Okay, so in the same way we can get a bound on the number of edges in terms of the number of nodes, we could also get a bound on the number of regions in terms of the number of nodes. And now, we can actually see something pretty important from this. And there's an argument here, which I think I do want to recreate and want to redraw kind of to nail it in, because I think this is an important kind of counting argument. But I don't know. I mean, have you guys seen loads of counting arguments in this class, or not really? Or yes? Too many? Let's see. Okay, so since the number of edges is less than or equal to 3n minus 6, then at least one vertex of a planar graph must have small degree. So in particular, at least one vertex of a planar graph has degree less than or equal to 5. And how would we show this? Well, we would show this with a counting argument. Okay, so assume not. If not, that means that every node must have degree 6. And this means that the total degree is greater than 6 times the number of nodes. What is that? So something is going on.
Somebody's nodding.
It doesn't, and I guess it's nice that it doesn't get onto the microphone. Thanks. That's not so bad. And because at least I can't hear it, right? Okay, so the total degree is greater than 6 times the number of nodes. And the total degree is so the total degree is 2 times the number of edges. So this means that 2e, the number of edges, is greater than 6 times n, which implies that the number of edges is greater than 3 times n. But that doesn't make sense. Now we've reached a contradiction. Because we know that the number of edges is less than or equal to 3n minus 6. So this is one of hundreds and hundreds and hundreds of counting arguments which you will see in your life. and it really, really is important to understand for almost all fields. Okay. So now we've described two or three important qualities of planar graphs. So what have we done? We've defined planar graphs. We've described a couple of different ways of viewing what we mean by a planar graph. We've shown that you can straighten all curved edges so that all edges are straight. Then we've looked at this relationship between the number of regions and the number of edges, the number of vertices. And then we said, well, actually, we can put a bound on the number of edges, showing that these graphs are really very sparse, that they've got to be planar. And the final topic on planar graphs that I want to talk about is, how do we know whether a graph actually is planar? I mean, is there a simple characterization of what we mean by planar graphs? And what we saw, if we review it from the last class, is in fact, for Eulerian graphs, there is a simple characterization. For Hamiltonian graphs, there is no simple characterization. And I think there's going to be time at the end of class for me to say a little bit more, just another really neat theorem about Hamiltonian graphs. And for planar graphs, there is a simple characterization. And I think it's so simple, it's just, I mean, let's just say the person who figured this out must have felt that he had a pretty good day. So this is called Kuratowski's theorem. And it says that there is a necessary and sufficient characterization of planarity. In particular, so Kuratowski proved that if a graph does not contain these two graphs, then it is planar. So the first graph is K33. It is a bipartite graph showing that all of these three nodes are connected to all of these three nodes. And the second characterization is that the graph K5 is not included in this graph, where K5 is just the complete graph of 5 nodes. That's pretty amazing. I think that's pretty. Is that amazing? I mean, you wouldn't have thought that there's such a simple way to describe whether you can draw something in a plane. And additionally, it's pretty amazing that it's these two structures which are forbidden, which don't seem, I mean, these seem to be fairly arbitrary structures, but just as long as these two structures are not in the graph, then we know that the graph is planar. If one of these structures is in the graph, then the graph is not planar. And and basically that's all there's to it. So Steve asks us the following question here. So by Kuratowski's theorem, this graph here must be planar. So the question is, can we figure out how to embed it? And probably I would like some help in this. So shall we try to see if we can do it? So I'd like someone should help me guide my pen. Verbally, of course. I can.
Number the nodes.
Yeah, that's a good idea.
Edges between 1 and 3 go straight.
Uh-huh.
5 and 3.
Mm-hmm.
And 4 and 5. 3, 4.
All except 2, 4.
Yeah.
So 2, 4, and 1, 4.
All except 2, 4 and 1.
Oh, and so this one here.
Yeah.
And then I guess we just,
1, 2.
so then we can just bring this around here. Bring that around there. That's right. Have we missed anything else?
No,
One,
we're missing,
two.
we're missing 2, 5.
I'm missing which one, sorry?
2, 5.
Ah, which means that I'm...
No, take 1, 4 on the same side as 2, 4.
Right. Yep, I crossed out the wrong one. So I think I'm going to redraw this. Okay, so now, so guide my pen again. So 2, 4 goes above the top.
Yeah.
And now we can bring 2, 5 around the top as well, right?
Yeah. Then 1, 2 straight.
And 1, 2 straight.
5 from the no.
You may put 3 in the center and put 1 up.
So we should put, so we could put 3 in the center, and then 1 shouldn't go here at all, should it?
1 go up 3.
So 1 should go here, right?
And 5 in the triangle of 2, 3, 4.
So we should put 1, 3 here, right?
Yeah.
So now we can go 1, 2,
3,
1, 3,
4.
and 1, 4.
And you put 5 in the triangle of 2, 3, 4.
So is this...
You make 2, 3, 4 as a triangle, that's the base. And you put 1 up out of this triangle and 5 in this triangle. And then
Okay, so 2, 3, 4 as a triangle.
yeah, and put 5 in the triangle. Yeah. And put 1 out of this triangle.
Like that. Right? Is that done? I think so. We may have permuted the numbers, but I think it's done, right? So there is a more to this. Right, because now if we make this 5, 1 isn't connected to 5, but everything else is connected to everything else. So there is a moral about this. And the moral is that it can be really, really algorithmically difficult, to figure out the right way. If you have a graph in the computer, you can see that it can be very difficult to find the best way to visualize it. And so this is actually a very, very important problem. It certainly isn't obvious that this structure here is the same as that structure there. And this also shows that another very, very important and very difficult problem is the problem of graph isomorphism. How many people know about this problem? And basically, suppose I input a structure for one graph in the computer, and then I change the names of the nodes and input another graph in the computer. So the question is, how can you tell whether these two graphs are actually the same graph? And this turns out algorithmically to be a very difficult problem, as well as a very interesting problem. And the reason algorithmically why it's very interesting is because nobody knows how to do this in polynomial time. However, at the same time, there is extremely strong evidence that it is not NP complete. In other words, this is a problem, one of very few problems, which is believed to be easier than the traveling salesman problem, but harder than a polynomial time, normal polynomial time problem. And this is the problem of graph isomorphism. And with this exercise of trying to draw this graph here, you can really see why this problem might be difficult. Actually, it turns out that in practice, it's pretty, in most cases, one can tell whether two graphs are isomorphic pretty quickly by using heuristics that work often. But in the worst case, this could be a very difficult problem. Okay, so this is Kuratowski's theorem. And I guess the last, okay, so that's Kuratowski's theorem. I guess the last point that I should describe about this theorem is, what do we actually mean by containing? And clearly, we don't mean just isomorphic. Because, I guess I will say it should be obvious that this graph here is not. Because even without this edge here, even with this edge missing, the graph isn't planar from the previous theorem. And so certainly adding an edge shouldn't be able to make it planar. The main idea is that dividing up the edges with extra vertices cannot affect planarity. In other words, we couldn't, since we allow, so here, the last point, we allow curved edges that in fact aren't necessary, but basically we could we could kind of divide this up with extra nodes here, and it shouldn't affect the planarity or not. So the final point about Kuratowski's theorem is that two graphs are homeomorphic if they can be obtained from the same graph by dividing up edges. And so the theorem says a graph is planar if and only if it contains no subgraph that's homeomorphic to K33 or K5. And this is an extremely beautiful and powerful theorem. But I guess I should maybe finish talking about this by just mentioning a couple of words. Who cares about planarity? Why is this important in the first place? And I guess there's several reasons why it's important. Yeah?
Can you go over the last page?
Oh, sure. So the main idea is that we can kind of take these edges. So two graphs are homeomorphic if they can be obtained from the same graph by dividing up edges. So maybe
do you prove K5 is not planar formally? Can we discuss?
That's actually, all right, excellent. I'm glad you asked that. I wanted to say that. So how would you prove that K55 is not planar? It's not very exciting. It's basically just case analysis. You know, you just basically try all possibilities. So in particular, I mean, the flavor of the argument would probably be something like this. You know, without loss of generality, you know, you can start with a triangle. And you might as well, without loss of generality, make these points 1, 2, and 3. And then I guess there's several possibilities for node 4. Node 4 could either be inside, you know, or outside, or maybe here, something like this. And so you would just sort of work through all possible cases, and show that no matter what you try, it doesn't work. You know, and then you do the same thing with K33. There might be a nicer way, but I don't think so. I think it's really just an ugly trying all possible things. But yeah, thank you. I wanted to say that. Yeah. So two graphs are homeomorphic if they can be obtained from the same graph by dividing up edges. And so a graph is planar if it contains no subgraph that is homeomorphic. So you know, just by dividing up edges here with a couple of extra nodes is going to affect planarity. Right, and I guess I'm just hesitating whether or not to say the same thing over and over again. I was just going to repeat Grotowski's theorem once more time. I'm not sure. Are there any questions before I switch gears, or anything that people want me to repeat?
Why you say it's important?
Oh, right. Okay, so it's so it's important for several reasons. I mean, you know, if the question is, if a student says, so why should I learn about planar graphs? So one reason, which I think in itself is sufficient, is that planar graphs are really beautiful structure. I mean, you see how much structure there is, and because there's just so much of it, something nice must be going on underneath. So that could be one reason. Another reason, which maybe is more convincing, at least to practically minded people, is that so many things in life are planar or very close to planar. So roads are, maybe maps are not quite planar, but they're pretty close. Or, you know, say you were trying to, I don't know, say you were trying to find a good routing algorithm to route packets over the internet or something like that. Well, maybe the internet is planar or pretty close to planar. And so using this additional geography, you can come up with a better algorithm. And so it turns out that there are many instances of problems which are very, very hard to solve in general, but if the graph is planar, it's much easier to solve. So say you want to, I don't know, as another example, transitive closure. It turns out that in parallel, like if you're trying to compute the transitive closure of a graph, I'll just say this, if you don't know what transitive closure is, it's not that important. But say you're trying to figure out the transitive closure of a graph in parallel. Well, it turns out people don't know how to do this that effectively. The best that they know how to do to compute the transitive closure is to square a graph, where sequentially you can sometimes compute the transitive closure much faster. So this is actually what's called the transitive closure bottleneck, which is that in parallel it's very hard to compute as efficiently as sequentially. But if the graph is planar, then you can compute the transitive closure very quickly. I mean that's just one example off the top of my head. Basically, there's a lot of very, very important structure, which means that things that are very difficult on normal graphs are easier on planar graphs. And planar graphs appear so much in daily life. Like you could view a map, the adjacency matrix in a map, like whether two states are connected, where, say, a map of the United States where states correspond to nodes, and there's an edge between two states, if the two states are adjacent to each other. So this is a planar graph. I mean, there's so many graphs in daily life that are planar. And because of this, it's important to understand what additional characteristics a planar graph has that one could potentially make use of in order to make whatever application you care about run faster. So this would be the practical as well as the theoretical reasons why we should all care about planar graphs. And in fact, there are some computer scientists who have kind of made a career of taking problems that are difficult in general and showing that on planar graphs they're much easier. So they're just computer scientists who know a lot about planar graphs, and just for every problem they see how much easier it is on a planar graph, and they can make a career out of that. Yeah, and it's a good career. I mean, this is a justifiable thing to do. It's not just a no, this is a good thing to do. It's one of these gaps in research which someone has got to fill, and a couple of people have been the first people to do this, and it's a good thing to do. So let's see. How much? I have how many minutes? 5 minutes left?
22.
Okay. So let me just make one quick final remark about what we were talking about last class. There was one more comment that I wanted to say. But I didn't. And I'll make this quick because a couple of people handed out exams last class. And for those who regrettably were absent in the last class, I can give them their exams today. But the main there's one more really neat thing that I wanted to prove. So in particular, I wanted to prove that if G is a graph, say containing more than 3 vertices, such that for all non-adjacent vertices, x and y, the degree of x plus the degree of y is greater than n. And in this case, the graph is Hamiltonian. So recall that a graph is Hamiltonian if you can find a tour that visits all the nodes in the graph exactly once and then starts and ends in the same place. So if you take any 2 vertices that are not touching each other, so the degree of this node plus the degree of this node here is greater than or equal to n. And in this case, the graph is Hamiltonian. What this theorem, how this fits in with what we were talking about last week, 2 days ago, not last week, is that although there's no necessary and sufficient characterization for a graph to be Hamiltonian, there are certain necessary conditions or sufficient conditions where if this condition holds, then you know that the graph is in fact Hamiltonian. And this is one characterization. And maybe I'll just give you the intuitive idea of the proof very quickly, and then you can read over the transparencies afterwards. Does that make sense? Okay, and I'm going to read this out loud, and I'll draw pictures. But this is a good, if there's something which people want clarified, then speak out. So we're going to prove this by contradiction. So assume the converse. In this case, there exists a graph that is not Hamiltonian, but where each pair of non-adjacent edges has degrees totally less than n. So for any pair of adjacent edges, the sum of their degrees is greater than n. At least n, not less than. Okay. So now what we're going to do is we're going to add edges to this graph until we can't add any more edges without making the graph Hamiltonian. So what we're going to do is we have this graph that is not Hamiltonian, but that's satisfied. By assumption, we have this graph that's not Hamiltonian, but satisfies the assumption that we were talking about. So now we're going to throw in edges, pepper in edges, until we can't add any more edges without making the graph Hamiltonian. And by Hamiltonian, we mean it contains a Hamiltonian cycle. So because of this, we know that the graph contains a Hamiltonian path. We know that this graph here contains a Hamiltonian path because this is what's required so that if we add one more edge right here, then the graph becomes a cycle. So that we know that we have a graph where if we add one more edge, it becomes Hamiltonian, and this means that already there must exist a Hamiltonian path. But now, it turns out that this edge here, this node here, is adjacent to a bunch of other nodes. This node here at one end of the Hamiltonian path, and this node here at the other end of the Hamiltonian path, is adjacent to a bunch of other nodes. But suppose this node here were adjacent to this node. This node on the right is adjacent to some node in the middle. And this node on the left is adjacent to a neighboring node in the middle. Well, this can't happen, because if it did happen, then we would have a Hamiltonian cycle, right? In other words, if ever this node, there were an edge from here to some node in the middle of the cycle, of the path, an edge from one end node to a node in the middle of the path, and an edge from this end node to the middle of the path. If ever these two nodes were next to each other, then we know that we can sort of splice things around and twist it like a pretzel and get a Hamiltonian cycle. So because this happens, we know, so we know that this can't happen. But now what you can do here and what you can read about is, well, we know that this node here plus this node here, together their degrees equal up to n. And this will actually lead to, and this actually leads to a contradiction, because if the degrees there lead up to n, then you get a Hamiltonian cycle. So the degree of this plus the degree of this must add up to no more than n plus 1. And this contradicts the original assumption. You can read about this, and this is the proof. The point about this proof was this is a beautiful characterization of a class of graphs that contain Hamiltonian cycles. And the other point about this is Professor Skeena asked me to cover it. I wanted to cover it. Let's see. I think I should end class now. I'll hand back exams for those of you who didn't get it last class. And maybe I'll see you in my class next fall, Advanced Algorithms, 548.